Welcome back. As announced this morning, the best paper award goes to the authors of automatic termination of for HBO. I think it's a very important paper because now we know how and when to terminate actually, and we don't have to wait maybe for days. So I think that that's a really important direction. I already talked with some of you during the breaks, and I got a lot of awesome feedback that you all also believe that this is the correct paper to award today. So I'm happy to hand over that certificate that, so maybe looking to the camera for a second, that we have a nice Twitter photo. Perfect. So then without further ado, I hand over, and now we learn about all the interesting details, actually.
Yeah, thanks a lot. Really great. Glad to present this joint work with my incredible authors, Hubin, Valeria, Aran, Jan, Andreas, Matthias, Cedric. Yeah, I really enjoyed it. So what's the work is about? It's about automatic termination for hyperparameter optimization. I mean, we've been talking today quite a lot about how important it is to set up hyperparameters for machine learning properly, right? But it can be kind of expensive problem, right? And generally it might be solved via some iterative procedures for finding the right hyperparameters. And here we're trying to explore and study the problem when actually it's appropriate time to stop this procedure. We formulated informally like that we are unlikely to improve and what it means, right? And what we mean by this, let's try to dive in and understand what we are doing there. So we consider HPOR here as a black box optimization, right? Importantly, and in general setup for black box optimization of some unknown function f, a learner would sequentially acquire some points gamma t, right? And would observe some noise perturbed results. For hyperparameter optimization, that would be some hyperparameters that would define a model. We would do stochastic gradient descent, right? For model training. And then it would observe some model loss. Importantly, I do plot the two black box and model training on the very same plot, on the very same slide, just to show that we do not go deep into the details of whether we stop SGD or not, right? This is a parallel orthogonal type of works. And here then, just getting back to the problem formulation, when we want to evaluate our model, we would train the model on the data D and compute its result on prediction on an input X, right? And then the loss would be computed with respect to true label Y. And we would like to evaluate it as an expectation over the data we haven't seen. In practice, what we evaluate is noisy evaluation, right? That comes due to stochasticity in the model training. So, and this is exactly the objective we would like to minimize in practice, right? And then maybe deploy the model in production. So Bayesian optimization is a powerful framework for such global black box optimization. And I will just briefly sketch the main building blocks of Bayesian optimization for those who are not familiar. In general, for some function f with a known optimizer gamma star, BOR would sequentially train a probabilistic model computed and over the point we have been already evaluated for the unknown function, and then acquire it again iteratively some new points, like the most promising points, the most promising hyperparameters to evaluate, and then update the model and continue such a sequential acquiring. That would last until, naively, until some user-defined budget, how much you want to invest, right, in optimizing such a model. And in practice, we would measure, if we could, convergence via the regret. That is basically just suboptimality in the function value. In theory, you could also go for some other metrics, right? Like, I don't know, cumulative regret, how your model, how your optimization performs over T rounds. But when we work with the model in practice, once we stop our optimization, we want to deploy it in production. And then this suboptimality, it actually the metric that would make sense, right? How good we would then, how the model would work in reality afterwards. And since this quite of an expensive thing to train the model, right? It would be nice to understand when it's enough, when could we stop already the Bayesian optimization procedure. There are some methods that require you to specify the budget in advance, right? Or some conversion tests that would also ask you to specify some value in advance. But what we are trying to ask is whether it's possible to define something on the run, when to stop it. And this is the question we are trying to address in the paper. However, before we jump into this question, I want to draw attention to the question whether actually f of gamma is actually the objective we optimize in practice. Yeah, the answer is clearly no, because the distribution is unknown, right? And what we can evaluate is only the estimator of this population risk of this expected loss. And in practice, that would mean that we are given finite amount of data set, right? And we evaluate our model on some validation data set. That would result in the fact that evaluation we observe there inherent stochasticity, not only due to the model training, right, but also due to the realization of the data. And while this is kind of an obvious thing, right, this discrepancy might affect the optimization procedure. Here we can see clearly that there is this inconsistency between the true HPOR objective, this population risk we're interested in, right, and the commutable BOR target that actually is optimized. And so again, then BOR in the very same spirit would be applied for this computable orange target, right, and would iteratively converge to some intermediate solution gamma T star. Again, measured by quantified by suboptimality in the function value. The problem occurs when the convergence in terms of the computable target yields suboptimal solution in terms of the objective we are interested in, right? And the first empirical contribution of our paper is like to study whether there is overfitting occurring to validation data, right? And I mean, the main takeaway there would be just actually longer, running Bayesian optimization longer might not only waste your resources, right, for model training, but also harm the performance and generalization performance you are really interested in. And that leads us to the solution and to the answer to the question, when should we actually stop intermediate SBO procedure? So informally, as I mentioned already, it's like saying that we are unlikely to improve the generalization performance. And formally, we would oppose it as following. So since f hat is an estimator, right, it's equipped with some uncertainty due to the data realization. And we depict it here nicely in this orange bold. Formally, that would mean that if the statistical error of the estimator is bounded by some epsilon esteem, statistical error, then we can bound the suboptimality we're interested in the population risk by this error plus the suboptimality in this computable objective. And the main takeaway of this inequality is that though though we can push more and converge the suboptimality in this f hat value to 0, that can be guaranteed, right, by many established BOR algorithms as t goes to infinity, we could not eliminate this fluctuation, right, that happens due to the error of the estimator. And then our empirical suggestion is then when these values are kind of comparable, right? There's no guarantee that there's going to be a substantial improvement in the population risk minimization. What does it mean to be comparable, right? It's a question, right? It's kind of an empirical suggestion. It can be 10 times, right? It can be 2 times, but what we suggest is more like an equality, right? More like a termination criteria that says, okay, once this simple regret drops below this estimation error, we would stop. We would say this is enough. Yeah, and it is formulated as one, the simple regret is dominated by the statistical error, estimation error. The only thing that neither the regret nor the error are generally known. Yeah, we cannot compute them. The value, the optimum values are known. And what I'm going to show in the next 2 slides is how we actually estimate these values. So the first one is the known regret. It might be kind of clear for those who work with probabilistic model how one can derive this bound. And it's based, again, on the Gaussian processes, or any, here we work with Gaussian processes, which is a posterior GP that we infer from the points that have been evaluated already, GT. And idea here is that as long as our F hat is some function that belongs to a class of reproducing kernel Hilbert space associated with the kernel of the GP, we can actually build hyperprobability confidence bound for this function, where the mu and sigma would be the one which are the parameters of the posterior in the GP. So yeah, visually that would be a nice confidence bound on our optimized function. And we can easily then show how to derive then the upper bound for the simple regret we are interested in. And visually it would mean that at this iteration T, we have new model, right? A new GP model. We minimize lower confidence bound over the whole domain. Then for each point over the domain, we can compute this the difference between its UCB and this minimum UCB, minimum LCB, right? And here we plotted in this gray. And then once we minimize over all the points we have evaluated so far, that's gonna be our upper bound for the regret we're interested in. Okay, so this was our first ingredient, quite easy. The second ingredient provides us with a full automatic framework, right? Though even with this first upper bound for regret, we can already say, okay, if a user has a predefined tolerance for the solution, you can just plug it in, right? You have an upper bound, you can compare it to this tolerance, and it's going to work somehow. If we want it to be fully automatic, we show how to compute this estimator error in case of a cross-validation, right? And this estimator error can be characterized in terms of a bias and a variance. And in case of cross-validation, we know, this is learned, a studied estimator, we can use then the theory that has been there already for years to estimate these values, variance of the estimator and bias. While bias can be neglected in case of cross-validation, the variance can be estimated as follows. So we are again coming back to this nice visualization of how the model training looks like, right? And now we have k-fold cross-validation that provides us with an estimator, and then the sample mean is used to navigate. The sample mean is basically evaluation of our unknown objective. As a byproduct of that, we can easily extract the sample variance, right? And then that provides us with a way to get an estimator for the variance of an estimator, right? It can sound a bit obfuscated, right? But we cannot know this variance for sure, right? It's gonna again require an estimation of that. So then this is just a multiplier that can be computed depending on your number of folds k and size of your data set. Okay, and so by this I finish the presentation of how the method works, right? This is our second ingredient that we can easily plug in, and then at each iteration t of Bayesian optimization, we could compute this value, right? And then use it as a way to decide whether we stop at this iteration or not. All right, so we evaluate this stopping criteria over a wide range of HPOR and NAS problems, both when we use cross-validation, right? And when the cross-validation cannot be used or just too expensive. And the first set of experiments is hyperparameter optimization of XGBoost in random forest over 19 tabular data sets. And how do we compare this method? How do we compare the methods? Yep. So what we use as metrics are relative error change and relative time change. So relative time change is its x-axis. The bigger it is, the more you save as a speed up. Relative error change means how better you are in terms of the test solution. So positive means you get better, and negative means you get worse. Relative, right? This word relative. Relative to what? We use just a standard predefined budget as a comparison to any other of the baselines I'm going to talk about. And this is 200 iterations, right? By 200 iterations, you check what your test error is, and you know your budget is 200. Okay, so yeah, as mentioned already, this is, I would say, quite an underexplored area, and not that many baselines, but those we could find we use. So the first of them is the convergence baseline, I, that checks how many iterations the best performance stays unchanged. So if it stays as changed for I iterations, in our case is 10, 30, 50, we stop. The second, I would say, even family of baselines are based on probability of improvement and expected improvement. So at each iteration, we compute these values and then stop if they drop below some values. Yeah, you can see here that the values of probability improvement and expected improvement are quite small. And this is one of the first drawbacks of this method. It's quite hard to decide in advance how do you actually set up this value, right? You would need to search for this value, but it's kind of not that easy to interpret. How do you choose this? Yeah, and finally, our methods are in green, where the threshold derived from cross-validation. Why there are two methods. So the one of them is just out of the box used stopping threshold that we derived through these theoretical guarantees, right? And the second one just shows us that actually, of course, you can a bit play with this parameter, because I think you remember, right? Because we were like thinking, what does it mean to be comparable values of an regret, right, and an error. So same for random forest. Oops. And yeah, what I would draw your attention to in this plot is that our method has lower variance in relative error change in comparison to the baselines. At the very same time, it has kind of a huge variance over the relative time change. And the conclusion we make from this is that it's nice that our method is actually really problem adaptive, right? It will not stop unless you really, it makes sense, right? And that would mean that for some problems where it makes sense to stop, it will stop. And for some methods where it doesn't make sense to stop, it will continue, right? It would lead, of course, to no change in time, but still we would be able to keep the quality of the test solution. All right, the second batch of experiments is where cross-validation is just expensive, right? And we have to stick to user-defined threshold. And in this set of experiments, we just apply the stopping criteria for TP, BOR, GPOR, and random search on two benchmark, NAS HPO bench and NAS bench 201. The baselines are still the same, except that our method now uses 3 types of thresholds, right? So you can see them here in the legend. Yeah, same for TPE. And yeah, just know that this is, of course, just a part of the experiments, right? There are many more of them. As a conclusion from this plot, what I would say is that what we observe from this plot is a Pareto frontier, right? It's actually kind of, I mean, it's kind of difficult to say which method exactly is better. Here we use the our method with the user-defined threshold, right? The user says what is his tolerance to the solution, and it provides him with a nice and interpretable navigation in this Pareto frontier. In contrast to other methods where you define number of the convergent iterations, that might be kind of difficult to define in advance for different type of problems. Right. This is the end. I want to thank my great co-authors and just again conclude what this talk and what this paper was about. It was about effective yet intuitive termination criterion that adapts to a problem, and it uses and exploits this inconsistency between HPOR true objective and the one we could actually compute. I'm encouraging you to check more experiments in our paper. So in this QR code, you can just easily navigate to the paper. And if you have any questions, suggestions, I'm happy to answer. Thanks a lot for your attention.
So who would like to go first? Alex, sure.
So first of all, congrats to the paper. This is very, very nice. Second, I think you've left a little bit of improvement on the table. So you're imposing an L infinity bound between your estimate and the truth, right? And then you're using the variance estimate to get that. But actually, you don't need that, right? You only need this near the minima of the objective. So if you replace the overall variance estimator with a localized one around potential regions, you might be able to terminate quite a bit earlier.
I think this is a really good question, right? And I think it firstly highlights the fact that variance of hyperparameter is different, right? It's not that it's homoscedastic, right? As we generally would naively assume in Bayesian optimization. And yeah, it is heteroscedastic, right? And for us, it makes sense then to estimate this value closer to the optima. I think it's a really good question. And I think what we also can do is not only use a point estimate then, right, near the optima, but just then assume that we are estimating a known value, right? And these are, again, evaluations, right? And yeah, just maybe use another level of optimization, but it might be well tuned. I understand it completely. And I think this work is more like, yeah, just quick show that it works. And if we can fine tune it, right, even more, it might make even more sense in theoretical sense, even more. Yeah.
Yeah, thanks for the talk. Very thought-provoking ideas. So what often happens in HPO for deep learning, for example, is that we do the HPO on the validation set, and then after we have an optimal hyperparameter setting, we then retrain again using also the validation data. Do you think that it might make sense to stop even earlier to reduce the overfitting to the validation set even more in the setting that are lined out? And how would we go about that?
Yeah, I mean, I think this whole question of how do we actually overfit, right? How to measure overfitting, like it's kind of a not well-studied problem, right? What we do highlight in the paper that it might occur, but still, I would not say it's kind of a clear. There is kind of a clear answer. How do we measure that? And I think as long as we able kind of quantitatively answer this question, that I would maybe provide a more reasonable answer. Otherwise, I would just speculate. Yeah, I don't want to do this.
So, sorry. So, thanks a lot for the talk. I'm also curious about the topic of overfitting. So, what's your sense regarding your proposed algorithm, and how, like, what observable results are there with regards to overfitting, and like how often is your sense that it actually occurs?
I think for this I would need to open the paper, right, and to show some plots. And I would maybe generally answer that it's just the fact that it might happen, especially when your validation data set, right? I mean, it just shifted in comparison to the test data set. And I think also, I mean, if we are really interested in fact how to deal this, maybe this early stopping solution might not be the general solution to this, right? And there are already methods in Bayesian optimization that would cover distributional robustness, right? And I think if we want to, solve it in a more principled way, this is maybe the solution and the way I would go. And our method, it's got discharged, unfortunately. Yeah, our method is more like kind of exploit the fact that if we know that it can happen, right, it can help, right, stopping earlier. So, thanks.
Yeah, congratulations from my side too for this really nice work that's opening a new topic for us to really think about more. One question I had was, you showed in the plots there was EI and PI, and well, there were with 10 to the minus 17, 10 to the minus 11. So of course, I fully agree that yours is much more interpretable and much easier to set a priori. Nevertheless, I would be curious if you could also get a Pareto curve with EI or with PI, and how that would relate to the Pareto curve that you get with different values for your method.
Yeah, for sure. We did an ablation study for all of the methods, right, where we would change the parameters, right? And I'm encouraging you to check that. The thing is that with the PI and EI, you would observe such a Pareto front. The only thing is that these values, they become really, really, really small, right? And it's just at some point, it just doesn't make any sense to make it even smaller, because you don't understand what's going on. Artificially, you could do this, right? And you would observe this, but practically, that's just something that, doesn't create a method that I would rely on. The papers, right, that use this method, and the papers we took these methods from, they also don't talk much about how they choose this value. And this is an extra, to this,
Okay, so let me maybe ask also one. That was black box optimization, right? What happens if you go to multifidelity optimization? Do you see any way to extend that to multifidelity optimization? Would you then use the lower fidelities actually, or only looking at the highest fidelity? How would you do that in that case?
Really good question. So it means that in some sense, like multifidelity means that we don't consider the black box, right? And we don't get just an evaluation of that, but we rather open, right, and maybe stop earlier. That would mean that the noise we are encountering, right, is just of a greater scale, right? I think, and then the variance, I assume then the sample variance would be different, right? And we would always need to know how. I would maybe suggest that in this case we would need to model the variance, right, of this estimator as a multifidelity function. So just if we getting back to the case where we use black box, right? We, in general, would assume, okay, it's homoscedastic, and this would be the simplest. Then we go and they say, actually, in some areas, hyperparameter variance is different, and then we model it as a function. And then we say, oh, actually, it's a multi-fidelity thing. It means that, basically for when we stop, when we stop earlier, the variance is going to be different. And then it's going to be kind of a multi-fidelity. I'm not sure whether there is this connection between the fidelities. I don't know theoretically how it works, but I would maybe try to dig and look at this area. Yeah, I don't know, maybe others have better suggestions. It's just, flow of my thoughts.
Maybe we can talk about that offline later on. Then thank you very much. Again, a round of applause for the speaker.
Thank you.
There are two things I would like to say at the very end for today. So we are more or less at the end of the program. So there are no other presentations today. One reminder, and Frank, please correct me if I'm wrong. Inside that room, everyone has to wear a mask properly. Please, guys. That's really only to protect us all that we are not getting to super spreader event. The second thing is, if you look now at the schedule, we have now 5 minutes break left because we are a bit behind the schedule. And then we're starting at Signal's Pavilion actually with a research speed dating. Katharina and Matthias prepared a very nice way that we're getting to know each other even better, that we're getting increasing our network, and they will tell you in 5 minutes over there how we can achieve that. So I hope that you all will participate. If not later, of course, we also have the reception and having nice food. So I hope you will enjoy the evening with us. Bye.